Good morning, folks.
Good morning.
How are we doing today?
Doing well, thank you.
Good.
How are you?
Oh, I'm doing just fine, thank you. Let's see, we've got what 9-2 due today. A test on Thursday. I'm grabbing up your tables here. You guys been looking at the null hypothesis stuff yet? Got some yeses there.
Instructor Haugen.
Yes.
For lab 4 and 5, I got the N/A, so I can't see my grade on those two labs. And I was wondering if you could fix that maybe.
Yeah, let me make a note.
Okay, thank you.
That's usually a setting on my side. Listed as not available is what the NA stands for. But usually that means it's being hidden. So I should be able to fix that. Yeah, that's usually a global setting. There's like 3 places I have to change that. One place changes it for individuals, the other place for but yeah, I should be able to fix that, no problem. Thank you for letting me know. Let's see, why don't you guys take a minute and look at this sample size question, kind of decide how you try to approach that. And then we can look over anything else specific that you would like to look at. And if there is anything else specific you'd like to look at, make sure you can let me know or put up a note so I can make sure we start looking at it. Yeah, it doesn't look like there's been a lot of starting to play with the hypothesis testing, but there's some. Okay. 2. It's similar to this one. These population ones, or sample size ones generally cause trouble. When in doubt, sample a couple thousand. So yeah, I think both of these questions are versions of number 14. It does tend to be a sticky section, a sticky problem. So we have an estimated standard deviation. Oops. We want a margin of error of 9 pounds. Confidence level 6.
So my problem with the deer one is, don't you need the sample size to determine the t value?
Yes, but of course we don't, we're trying to find sample size, right?
Yeah, which is where the knot is.
Which is where what is?
The knot, the problem.
Oh, the problem, which is why it's like, well, what do I use for that? Well, essentially, we've got to go, okay, the critical value, you're right, this is a Z value, right? And because we don't know the sample size, it's all we have.
So is it like using the worst case in the proportion, we just use the biggest Z-score we can find?
Yes, except unfortunately, this is almost the worst case scenario because the Z value of 2.05 assumes we have a large enough sample size that using S isn't causing a problem. Essentially, it's the t-score that's the best case scenario, not the worst case scenario. So in practice, what you usually have to do is kind of go, okay, we're going to use this score to give us a base sample size. And if that sample size is really small, like if it was 10 or 20 or 30 or 40, then you'd go, okay, given that range of sample size, you'd build a t-score, or you'd use a t-score for that range and then recalculate. And you can keep doing that to get kind of whatever accuracy level you want in your sample size. But in true practice, what you generally would do is use this value as kind of a baseline and then go, okay, I'm gonna add 10% or 20% to my value just to make sure I'm in the best range possible. Does that seem reasonable?
So when we don't have the sample size, we just use the z-score for the proportion that or the 0.96 or whatever.
Yeah.
Okay.
Because we don't have anything else we can use. You're right, that does bring in some error, but we try to compensate for that. But for us, we're just like, what would it calculate out to be? It would calculate out to be this. Okay, that's where we're going to start our argument in a larger context.
So the 2.05 comes from the 0.02 in the Z value?
Yep. So I just used that chart you guys have. You could use a calculator as well, I suppose. So the 0202 is the closest thing on the chart, and that's at negative 2.05. So yeah, that's where. And usually when we do that, we've kind of drawn the diagram. We want that to be a 0.02, so that makes that critical value the 2.05. And of course, that 0.02 is either tail when there's 0.96 in the middle. So since our margin of error is supposed to be equal to our critical value times our standard error, so our margin of error is supposed to be 9, the critical value of 2.05, with a standard error of the 25 divided by the square root of our sample size. That should give us a ballpark to start in. For figuring out a sample size. And yeah, as I said, these two problems are essentially both versions of that same question for 14. So the setups should be similar. You know, the confidence interval is higher, or confidence level is higher here. This 76, we really don't need. And again, just like the one above, we'd like to use t-scores, but we don't know what sample size we're looking for. We know it'll be more than 40. And usually you'll notice, usually these sample sizes are quite large. They're usually things where we get pretty close to that Z value anyway. I think this one's something like 1400 or something. So it's going to be pretty close to that critical value anyway.
Just a quick question.
Yeah.
So for that second one, it's going to be pretty big because I think I got the right answer. But the first one, because the confidence level is so like relatively low compared to, I guess, what is optimal, would it be a significantly smaller sample size?
I'd have to see what it actually ends up being.
Okay.
What do we get here? We get, well, whatever 9 divided by 2.05 is. What's 9 divided by 2.05? 4 point something.
4.39.
0.39 equals 25 over the square root of n. So then at any point you'll want to flip these. 1 over 4.39 equals the square root of n over 25. So multiply over that 25. So the square root of n is 25. Again, you could have divided that off first, but then people tend to lose that 1 on top over 4.39. You can also multiply both sides by the square root of n and then divide the 4.9 or 4.39. It's all up to you. Or you could use that formula that your text gives you, whatever you like. So what is that value?
I got 32.43. Since the sample size, I guess it'd be 33.
So it would be 33. Now I'm just going to check and see what, were they happy with the 33 or do they want you to go back and do something more complicated? I think they were happy with the 33. They should be happy with I hope they're happy with the 33. Because yeah, you can go back and continue to refine that. You could then go, okay, if I'm in this range, then my t-score is going to be more like whatever that t-score would be. And you can keep going back and forth until they kind of, and until the value stops changing. But in practice, you'd go, okay, let's go get 50. That'll be big enough. So I'd be surprised if they want anything other than that 33. This was number 14, right? Oh, not on yours though. Can't remember where I got this problem from. That's not where I got this problem from. Where did I get this problem from? Okay, I don't know where I got this problem from. Check. But I know for me on my tests, that's the answer I want. So. Where did I get this problem from? It's gonna bug me.
I think it's from 9.1, isn't it?
No, not with a mean in there. Oh, I know where it is. Never mind. I think. I've thought that twice now. Ah, yes, there it is. Yep, they wanted the 33. Good. This is a number 16, where this is a number 14. Same basic type of question, just written slightly differently. But yeah, you noted that they're the same problem. They are basically the same problem.
Can I talk through the number 14? And
Absolutely.
see where I'm going wrong? Okay.
Mhm.
So we have, so the equation we're using is standard error equals t times s over root.
Margin of error. Margin of error, not standard error. Yeah, these are
so
critical value. And you said s over the square root of n, right?
Yeah.
Okay.
So we have 0.4 equals, the critical value I got for this one was 2.708 from the table, times 6, which is s, over the square root of n or x or whatever you want to solve for.
Right.
So using algebra rules, we have 2.708 times 6 over root n, so equals 0.4, and then you can, through the magic of algebra, move just n over and replace it with 0.4 and have root n equals that fraction, and then you
Equals
square the
6.
fraction.
Yeah, you can do it that way.
Yeah.
Through the magic.
Over 0.4, yeah, and then square that. And I get 1650 for the sample size.
Oh, okay. I think I wonder if that's why. That would make me grouchy if that was why. But let's find out.
I've been banging my head against the wall on this problem for like 4 hours. And I'm sure I have the process right.
Yeah.
Yeah, I
Oh,
got
it certainly
17.
sounds like it. And then square that, you're going to get 16 and change. Yeah. But no, that wouldn't change it because, so let's say, for example, they said, okay, they wanted to use a t value instead of this value for z because the sample size was 40, right?
Mm-hmm.
Wait, 2.7?
Yeah, I used the t value for 39.
Okay, that's what's causing that problem. As I said up here, we don't have a sample size, so we don't want to use t, right? You're assuming a sample size of 40 for the big experiment.
Gotcha.
Fair? It's not going to be 40. The sample size isn't going to become 40. So this 2.78 is larger than necessary. Usually it's what, 2.56 or something like that? 2.54, I don't remember what it is off the top of my head. I should, I suppose, but I don't. Where's my cursor? There it is. 99 is 2.57, 2.575, 2.575. And that's going to lower that value and should give you the something around 1400.
Okay, yeah, it's 1492.
1492. Okay. That was actually one of the reasons I was looking at this problem going, well, we don't need this number and we don't really even want to pay attention to that number. The only things we needed was this, this, and this.
Yeah, those seem like a bit of red herrings.
Yeah. Or apparently purple in this case, because the color's not purple. But yeah, those are just there to distract you.
They do it really well.
Yeah. And I think in some ways that makes 16 a little bit easier, because 16 is saying, let's see, you estimate the standard deviation at this rate. There was no preliminary sample. My question would be, well, where did that 25 pounds come from? And there's a couple different places it could come from. A preliminary sample is one of them. That it's important not to let this preliminary value affect this stuff too much. You can see it added 200 people we had to survey, right? And if you wanted to go back and go, okay, for around 1400, what use that T to get a better approximation, that would give you a little bit higher value, but not near your 1600. Fair? So it would kind of balance it out a bit. If you wanted to go, this text isn't making us do that at all, but if you wanted to refine it that way, you could. One of the other ways to get this, by the way, I want to mention, because it does come up sometimes. If you, let's say, how many would that be? 150. This is pounds of deer. So let's say the smallest deer you found was 200, and the biggest deer you have found was 350. That gives you a range, right? Of 150 here. If we assume normal distribution, how many pieces or how many standard deviations is this range going to be cut up into? It should be cut up into 1, 2, 3 above and 1, 2, 3 below, right? For 99.9% of our population, technically 99.7% of our population. So if you break it up into 6 pieces. So one of the ways to get a preliminary guess at what your standard deviation should be for finding things like sample sizes here is to take that range of 150 and divide it by 6. That 150 divided by 6 is 25 pounds. And that's a very common way to get a gross estimate of what my standard deviation might be before doing sampling. What's the smallest I expect? What's the biggest I expect? So at that point, we're using a very gross approximation for standard deviation. We're using a critical value that we know is smaller than necessary because we only have z-scores at this stage. So that 33 is a real preliminary value. Fair? In a practical application, you'd go, okay, that's my minimum. Let's go 35 or 40 or 50, just to make sure we don't have to do this again. Fair? This 1400 is a little bit more trustworthy, one, because it's higher. So the error brought in by using the Z instead of the T is less. And this standard deviation is coming from a sample of moderate size. So I trust that standard deviation more than somebody thinks it's 25. Okay, how good is that? We don't know.
Can you go over how you find the critical value on the calculator again? Like which one you plug it into?
Sure. I would answer that by asking a question because that's always fun, right?
I have a question, even though I was late. Sorry about that. Are we going to go over 10 at all today?
Yep.
Okay, perfect.
I think somebody up there asked about 10, 1, 2, and 3. Does that mean we're not going to review Wednesday or not do? Yeah, we're going to talk a little more about 10 in a minute. So the key to figuring out your critical value is figuring out the size of that tail.
Yeah.
So, and that's that 100 or 1 minus your confidence level divided by 2.
Mhm.
And then since we know the area there, we know the proportion we want, and we're trying to find a value, that's our inverse norm direction, right?
Yeah.
So that 0.02 with the 0.1 will give you the 2.05 about. It'll be slightly different because it's rounded.
Okay, cool. I forgot that. Yeah, the mean. Didn't know a value to plug in for the mean and the standard deviation. Well, the standard deviation I knew, but the mean I wasn't sure. So we can just use 0 and 1.
Yeah, because this is a z-score, and z-scores live on your standard normal.
Okay.
Cool.
Yep.
Cool.
Awesome. Thank you.
Let's see. Yeah, the tables on the week 8, where you find that table. Good, but I wonder where to find sheet 2. Yeah, that chart doesn't have 96, so we have to actually compute it. But once we do, we could add it to that chart, and then we never have to compute it again. I think we've done 96 a couple of times too, so we should probably put that on the chart at some point. Okay. So in a lot of ways, this is great. The big thing you guys are asking about 9.2 are these sample size questions. And those are the nastier ones, partly just because there's some solving to it, and partially because there's all these kind of like, well, what are we supposed to do with the stuff we don't know? And the short answer of kind of ignore it and pretend it's not a problem is always a little bit of a weird answer. So, these are perfect questions for you guys have been doing a bunch of this and you're doing good, just some little details. So that gives me a fair amount of confidence that you guys are doing okay.
I'm taking physics right now, so ignoring things I don't like is starting to become second nature.
Oh yeah, physics. So yeah, pretend pi is 5 and just go with it.
Let's assume that there's no gravity on Earth for a minute.
Right. Because it's inconvenient. So we've talked minimally about chapter 10 being really just a vocabulary change of the things that we've been doing. 10.1, I think, is the kind of the nastiest one because it's got the most kind of new vocabulary and new kind of ideas. Nothing terribly mathematical, but new ideas in how to label everything. So let's spend a little time talking about that and then look at what we're going to be doing in 10.2 and 10.3. So chapter 10 is about null hypothesis testing, which at least sounds really cool, right? What does null hypothesis testing mean? It means essentially testing if things are different than they should be. I'm going to say standard. Just different than what somebody claims they are, different from what they have been in the past, different from what they should be in one way or another. So, for example, a machine is meant to put out 350 milliliters of soda for drinks. That's what the machine is built to do. That's what it's supposed to do. That's what it's set up to do. Fair? John, why not? John thinks it puts out too much, or puts out, I'm going to say, more than that. That means John thinks what's going on is different from the standard, right? That this machine puts out more than it's supposed to. Fair? And we want to test that. We need to test this. So to test this, we want to label, or in null hypothesis testing, we want to label what it is exactly we're assuming is true and what it is exactly we are, the alternative we're saying might be true. So the null hypothesis is the null for no change. I'd say status quo if I was confident on spelling status quo.
I believe you can do it.
No, you know I can't. Status. Your neon? No, it's no neon. But quo? Is that status quo?
Nice.
Really? Oh, good for me. No change, status quo. That's what is supposed to happen. And it's labeled H for hypothesis, sub-0 for null. So the no change, the standard, the basic hypothesis, things are what they're supposed to be. It's essentially our assumption. In this case, our assumption is that this machine should be putting out, on average, 350. So our average should be equal to 350 milliliters. Now, yeah, it might sometimes put in a little bit more or a little bit less, but it should be averaging centered around 350. Fair? So if somebody asks you to write a null hypothesis, that's what a null hypothesis looks like, and it should be your assumed status quo. That's essentially what we have to beat if we want to prove John right. Fair? Then we have an alternative hypothesis. That's the if things are different. And usually that's H sub A for hypothesis alternative. I think your textbook likes A1, or sorry, I'm H1. I have to check again. I forgot. I usually use a couple different books for references here. So, but either HA or H1. I always like the HA for H alternative, but if your book uses H1, it's the same thing. And that's what's being claimed. Fair? So what's the claim? The claim is that the average, specifically in this case, is more than 350 milliliters. Fair? So that's our alternative hypothesis. Now, the job in 10.1 isn't to actually do any of this testing. The job in 10.1 is to get familiar with this kind of vocabulary. What a null hypothesis is, what an alternative hypothesis is, and what our goals are, what we're going to be showing. Fair? So some language associated with this type of test. This is a one tail test. Why is it a one tail test? Well, what should be happening, our null hypothesis, says we should have a distribution that is centered around 350, right? And for any sample size, we might get some that were smaller and some that were larger, but most should be within a given set of standard deviations from that mean, right? Or technically standard errors from that mean, because we're in a sampling distribution. For us to say that John is right, that John is correct, that the machine puts out more than that, we would have to get a result that's not just more than 350 if we took a sample, but it would have to be significantly more than 350. Fair? So it would have to be out into this tail somewhere for John to be right. If we took an average and got 351, well, okay, 351, that's more than 350, but out of our sample of 50 drinks, that's going to happen sometimes, right? 351 isn't going to convince me. Well, how much would convince you? That's one of the questions we have to answer in doing this testing, is how far out into that tail does it have to be to convince us? And that's going to be based on our significance level. But that significance level should look a lot like a critical value, right? And it is. The significance level will give us critical values, and we'll be trying to see if our sample that we take is far enough into this tail, is past that critical value, then we can say we're going to reject that this thing is 350. Now, why is this a one tail test? Because we specifically are looking for greater than. So we're only looking for stuff to be out in this one tail. If John's claim was just that it's off, it's not 350, then this alternative hypothesis would be that the average is not equal to 350. In which case we could be in either tail. That would be a two-tailed test. Fair? If John's alternative hypothesis was that this thing puts out less than 350, that would also be one tail, but it would be on the left, right? This is specifically not only a one-tailed test, this is a right tail test. because it's on the right. It's the right tail. Cool. So you'll get some questions like that. That'll be like, read this problem and decide if it's, what's its null hypothesis? What's the alternative hypothesis? Is it left tail? Is it right tail? So that's kind of where you'll start. And you'll have other problems like the CDC says I shouldn't use CDC in this climate, but I'm apparently going to, says how about drug works 90% of the time. A group of some sort says they are wrong. Says they're wrong. No. And if we're going to test that, what would our null hypothesis be? What's the assumption we're going to make and test?
Maybe that more than 90% are wrong.
Well, our assumption is what we're told happens, because we're trying to see if these people are right or wrong, right? If these people are incorrect, if this group is incorrect, for us to say that the CDC is wrong, we have to kind of assume that they're correct. Essentially, when you think about null hypothesis testing, it's always kind of an assumption and then a claim. If you want to prove somebody is wrong, you've got to essentially prove that in their world. I am the CDC, the Center for Disease Control. That's a very big, serious organization. And we have claimed this. We claimed it's 90%. For this group to argue, not only do they have to show that any experiment they perform isn't 90%, but it's got to be significantly different from 90%, right? They can't get like 90.2 and say, haha, you lied. Well, no, that's just, random chance in your sample, right? The goal in hypothesis testing, and this is really important, the goal of hypothesis testing is to reject the null. You want to see, is there enough evidence to say that the basal assumption is wrong? Fair? And our conclusions, once we get to 10.2 and 10.3, our conclusions are either going to be there is enough evidence to reject it, or there is not enough evidence to reject it. That's it. We either reject the null hypothesis or there's not enough evidence. We don't even get to say this evidence supports the null hypothesis because you've assumed the null hypothesis. It's not fair to say, look, if you assume I'm right, it shows I'm right. That means I'm right. No, it doesn't. It means I haven't proved you're wrong. Fair? We want to say, is there enough evidence to show what these alternative people are saying? Is there enough evidence to show that it is not equal to 90%. To some significance level. For some significance level alpha. And for the sake of this problem, let's say alpha is 0.1. If alpha was 0.1, well, our sampling distribution, we know, would be centered around our 90, right? Under the assumption that 90 is true, which is our assumption, from the hypothesis. How many tails is this? Well, they just said not equal, right? They didn't say less than or more than, they said not equal. So that could land out in this tail. If it lands far enough out in this tail, then we could say, no, that's not going to happen by chance, you're wrong. If it landed way out in this tail, we could say, that didn't happen by chance, you're wrong. If it lands in the middle, near the 90, we'll say, we didn't have enough evidence to reject you. Fair? At a 0.1 significance level, 1%, or yeah, sorry, that's a 10%, right? This would be the equivalent of a, well, of a confidence level of 90%. That would mean there'd be 5% there, and there'd be 5% there, right? Could we, if we wanted to, figure out what the critical values for those are? We actually know what the critical values are for those. They're 1.65. 1.65. Fair? So if these people, if this group is going to say that the null hypothesis should be rejected, they've got to go test that. So they go test. They test, say, 200 people. And find that, let's say 184 times it works. Fair? And the question is that enough to reject the null hypothesis? Does this say that they're wrong? Well, what's their sample proportion? 184 out of 200 is what, 0.92? Well, that's 2% above. Is 2% above enough to be in these ranges? I don't know. Where are those ranges? Well, do we know what the standard error is here? It's a proportion problem, right? What's the standard error for a proportion problem? The square root of the PQ over N, right? You guys all say confidently. Now here's a question that often gets people in trouble. What's our P in this problem? Your choices are 0.92 or the 0.90?
Is it 0.92?
This P should be the proportion of the population, right? What are we assuming the proportion of the population is?
Oh, 0.9.
It's the null hypothesis. Fair? And again, that's the, you've got to prove I'm wrong in my world. Fair? So that 0.9 is our assumption. So 0.9 times 0.1 divided by the sample size that they used. So that's what, the square root of 0.09 out of 200, which is, oh, that's not it. I'm just going to calculate that. Hurt my little brain if I try to do that. 0.09 divided by 200 square root 0.02. 0.02121, so on, so on. So that's the standard error for this scenario. So how many standard errors are we allowed to be? We're allowed to be within 1.65 standard errors, right?
I'm sorry to interrupt really quick.
Shoot.
I got 0.21. Unless I'm doing something wrong.
Did you put 0.9 or 0.09 on top?
Yep. Okay. I see.
Cool. Yeah, that 0.1 is deceptive. So that means to be in this critical range, the critical range is the range outside either above or below, and we're above here, so we'd be targeting this upper range. We have to have this be more than 1.65 standard errors out. Fair? Well, how many standard errors out is the 0.92? Well, that's essentially what is the z-score for the 0.92. And that's supposed to be its value minus the assumed mean divided by standard error. It's essentially a z-score in the sampling distribution. They don't call it that. They call it a test statistic because they like giving things fun names in this section. But the test statistic is a z-score in the sampling distribution. So that's 0.02 divided by 0.02121, which is going to be 1 point something little, right? 1 point, I don't know what it's going to be, but pretty close to 1, right? No, it's not even going to be close. 1, it's going to be even less than that. It's going to be like 0.9 something something, right? Because it'll be a little bit less than 1 because that denominator is larger. Fair? Well, if it's a little bit less than 1, where is it? A little less than 1. If that's a z-score of 1, it landed right there. Did it land in that critical range? No. The critical range being the outside. Did it land in the I'm going to say you're wrong ranges? It did not. So, is there enough evidence to reject that hypothesis? No. So we would say there is not sufficient sample evidence to reject the null hypothesis. If it had been more than 1.65, if it had been out in that range, then we would say there is sufficient sample evidence to reject the null hypothesis. But those are really your only two possible conclusions. There's enough sample evidence or there isn't enough sample evidence to reject the null hypothesis. So that's kind of a real quick version of 10.1 and 10.2, frankly. 10.1 goes into most of this language. 10.2 starts us actually testing things. 10.3 starts to bring in p-values, which you'll read about, we'll talk about on Wednesday if you want. It's not really different. It just, I don't want to overwhelm you guys. The p-value, instead of figuring out, well, is this in some range? The p-value figures out, okay, for this test statistic, what is the proportion under that or after that? And you're comparing this to your significance level. So instead of saying, hey, is this value less than my critical, you'll say, is this area smaller than the critical area? It's the same question. It's just asked from a different perspective. So, and that's why I've said for, as long as we've been mentioning 10, nothing in 10 is something we haven't done. Really. It's just a lot of language. Fair? I've also said we're not going to hit 10 very hard on that final. Mostly it'll be, do you understand the idea of these confidence level, or sorry, the idea of what a null hypothesis test is. If it was up to me, I'd probably stop with this, you know, what's the critical value and what's the test statistic. But it's nice to go a little further with that. And why? Mostly because null hypothesis testing is a very standard set of tools to use. You will read a lot of papers and a lot of surveys and studies that will mention, even if they don't put a lot of things in this null hypothesis testing language, you'll hear those p-values a lot. It's like, well, what do those p-values mean? The p-values mean somebody has done this hypothesis testing. And that small p-value means you're way into that tail. So if somebody says, oh, I got a p of 0.00041, you go, dang, that's a small p. That is way, way into that tail. I feel very confident in rejecting this null hypothesis. If somebody goes, well, my p was like, 0.5, go, your p was 50%, no way. Go, you're full of crap. So being familiar with that enough is helpful as we go along. You guys are being very quiet. Tell me, was this overwhelming, or was it like it's weird vocabulary, but it all seems familiar?
To be honest, this section makes the most sense to me out of everything I think so far. Like, it's weird, like vocabulary, but the how you put it all together from like what they ask you kind of is a little bit more linear than some of the other stuff, I think.
Good. Well, and in some ways, this is very much, here is a process. So looking at it as being very linear is good, because this is we're not talking about a theoretical idea here. We're talking about a process that is extremely practical. And this is how it's actually used all the time. So that's good.
I
But-
have a quick question for you actually.
Shoot.
Just in regards to like with the final grades and everything, I keep checking the grade book and the last two labs have said NA for a while. So I'm kind of just curious, like I don't like right now because when it says NA, I think it drags down my lab grade total because it's like acting like I didn't get points for him.
I haven't, somebody mentioned that earlier. I have a note here to check that.
okay,
I tried to
awesome.
change those, but I'll go. I have a class right after this, so it'll probably be a little bit later this afternoon.
Yeah, no worries.
But I'll
I
figure
just-
out why that's happening. And if it stays that way, let me know, because I can change it on my end, and I've tried to change that on my end, but I can't see what you guys see. So sometimes I'll try to change stuff and it won't take for whatever reason. And I don't know that it didn't take. So
Yeah,
if that
so-
doesn't change by sometime later this afternoon, let me know and I'll.
Okay, awesome. And then I just
It was a
wanted to
bigger number.
ask, the last test, the final opens on December 3rd still?
Yes.
Okay, awesome. Thank you.
Also for the homework 9.2 on question 11, I think there's a little writing portion that you have to grade personally.
Yes.
But okay, cool. I just wanted to make sure on that.
Yeah, I always wait for those until after we're done, after it's done due. 'Cause that way I don't like grade some people's and like whose did I grade and whose did I not grade, and it gets crazy. So-
Perfect. Thank you.
Are we having a review for the test number 3?
On Wednesday, we'll talk about whatever you guys want to talk about. So if it's more on the null hypothesis stuff, then we'll talk about that. If there's review stuff that you guys want to ask, you can ask that. I will respond to whatever you guys want.
Can you
if-
touch on the lab 5 at all? Or the last lab,
Today or on
just
Wednesday?
now, just to
Now?
touch on it, just a touch?
Sure. Let me try to grab it. Also, I can, if you guys want, we can schedule a meet on Thursday if you want to go over anything else before the test. Just let me know who's interested in that, and I can do that.
That'd be
Happily.
fantastic.
Yeah, I'd be perfectly happy to do that. Let me grab that. And even if that's just a couple of people, that's great.
Yeah, I'm interested too. If no one has objections, I would, if it works with your schedule, Mr. Haugen, can we just do it at this time again? So 11:40?
Yes, yeah.
Okay.
Okay, what about lab 5, Christine? Christy, you were asking about lab 5, what particular?
Yeah, I just wanted you to kind of go over just the basic of it at all. I haven't touched it yet. I just wanted to kind of go over a little bit.
Okay. You're going to be making one of those confidence intervals based on our data. You can use the data analysis or descriptive statistics tools. As you guys know, the data analysis, that big data analysis tool, I am not the biggest fan of. So if I was to go through it, you'd have to have, obviously some data here, right? And if you wanted to use that descriptive statistics or tool, you could. Have I got it on this one? I don't remember. I think I purposely kept it off of this. So you can use that tool if you want to, but again, if it's me, let me put some data in here. How do we find a confidence interval? We find and average, right? Right, you're finding an average. So, oh, I don't want some. I want average, which I could type if my keyboard was closer. Okay, fine, be that way, I'll just type it. Average of that data. And then for our particular, we want 95%, so we would need a critical value. What's the critical value for 95%? 1.96, right? And then for standard error, we know the standard error for, well, I guess the critical value should be a t, shouldn't it? So what's the t-score for 95 for 1, 2, 3, 4, 5, 6, 7, 8? That's kind of fun. So, oh, there, yeah, t right there. So sample size of 8 means the degrees of freedom of 7, and 95% is the 0.025 on the right tail. So 2365. So, oops, sorry, I'm trying to do this fast. 2.365 was the critical value because it's a t, right, Christy? Okay. And then our standard error would be our standard deviation. So I would need that first. So our standard deviation for that, stdev.s, standard deviation of our data. And you could do that all together if you wanted to, but I'm going to do it in pieces. Standard error is supposed to be equal to the standard deviation. So that divided by the square root of the sample size. And you could use count to find the sample size, but I'm just going to put it in 8. And square root means raised to the 1/2 power. Or you could use the square root tool. Yeah, it all depends on what tools you want to use. Fair? But once we have that, then our lower bound should be our mean, which I suppose we could put that there. Oops. I'm doing too many things at once. So should be our mean minus our standard error, or sorry, our critical value times standard error. And then the upper one would be our mean plus our critical value times standard error. And we could put the mean there if we wanted to. The margin of error is the product between the critical value and the standard error. So we could just put equals critical value times standard error. And we could build all of those pieces. Fair? Now, the data analysis tool does have a confidence level tool in it. The problem with that confidence level tool is it works for 95% confidence intervals and nothing else. Fair? And that's the problem with that data analysis tool or that descriptive statistics big tool for anything. It gives you what it gives you and there's no fluctuation. Fair? if we want to do others, we could modify this any way we want. You can grab any critical value you want for any confidence level you want and not be stuck in what the descriptive statistics tool outputs. Fair? So if some of you guys are looking at all this and going, well, why don't you just like click, highlight, click, and then write all that down? Because I like the flexibility of knowing what we're, actually building. Fair? Oh, I lost Christie as I said fair. Questions about any of that before I let you guys go? I do have to get to that other class. Okay.
All right, thank you, Mr. Howdy.
Sure. And for those of you who've done more on Excel and are thinking, yeah, but you could find that there's a T-score tool, so you can like not have to use the chart. Absolutely, use any of those tools that you want. This is just the like least Excel knowledge way to go about this. Fair? All right. So I'll see you guys on Wednesday. Let me know if you need anything in between.
Thank you. See ya.
Sure.
Oh, I hope you had a good birthday, by the way.
Oh, I did. Thank you.
Thank you.
Thank you.
Bye-bye.